This is the first video for section 3.8 on more modular arithmetic and public key cryptography. In this lecture, I'll be talking about affine and multiplicative ciphers. So in the previous section, we were talking about ciphers that were based on the idea of addition and subtraction with modular arithmetic, where the modulus was 26. So every letter of the alphabet was assigned a number between 0 and 25, and then we would do operations, either adding or subtracting. And if the result of that operation would give us a number outside of that range of 0 to 25, we would divide the result by 26 and look at the remainder. Now, we want to look at multiplication in modular arithmetic, and there's at least two ways that we can incorporate that as part of an encryption process. An affine cipher would be a cipher where we would multiply by a constant number and then add a possibly different number. In a multiplicative cipher, it's a little bit easier, simpler, we just multiply, we don't do the adding part. So as an example, let's encrypt the message attack at daybreak using the affine cipher multiply by 3 and then add 5. So because we're going to be using our same alphabet arithmetic that we learned about in the previous section, I'm going to go ahead and write out my alphabet. And remember that we assign numbers to the alphabet where A is assigned 0, 1, 2, 3, 4, 5, and as usual, I group these in groups of 5 to make it a little bit easier to get the numbers going. So I write out my message here, attack, and I'm just going to start with the word attack. We can do the rest of it as we go forward. But again, the idea is to multiply by 3 and then add 5. So A corresponds to the number 0. So the calculation I'm going to do is multiply that number by 3. I get 0. And then I take that 0 and I add 5. That's going to give me 5. So this A is going to get encoded or encrypted as the letter corresponding to the number 5, which is the letter F. For T, T is here in my alphabet, 16, 17, 18, 19. So T corresponds to the number 19. So the operation I'm going to do is to take 19 and multiply that by 3. So time to grab my calculator. So 19 times 3 is going to be 57. And then I add 5. That's the second step of my process. So I get 62. Now 62 is too big, so we need to use modular arithmetic. So we take 62 divided by 26. Remember, we're finding our remainder here. That's going to give me 2.384. And then I take the whole number part, multiply that by 26. That's going to give me 52. So I take my 62, subtract the 52, that's going to give me 10. So the letter T, corresponding to the number 19, gets encrypted as the letter corresponding to the number 10, which is the letter K. So it's a little bit more complicated, but it's the same kind of finding remainders that we've been doing before. Now, the next T in my message also corresponds to the number 19, which means that's also going to get encrypted as the letter corresponding to the number 10, right? This arithmetic is going to work out the same way, so T is going to get encrypted as K again. And this A, again, corresponds to 0, so again, this is going to get encrypted as the letter F. So this is, once again, a substitution cipher. Once I know what any individual letter of the alphabet gets encrypted as, it's going to be consistent throughout the entire message. Let's do one more. C is corresponding to the number 2. So my operation is to take that number, multiply by 3. That's my first step. It's going to give me 6. And then add 5. So 6 plus 5 is 11. 11 is between 0 and 25. So I don't need to do any remainders. I can just use the number corresponding to the letter corresponding to the number 11, which is L. So the C in my message gets encrypted as the letter L. So I continue in this way. So here's the full encrypted message. Again, FKKFL was what we had so far, and then here's the rest of the message, all done the exact same way. Okay, so how would we decrypt this message? How would we decrypt a message that was encrypted with the multiply by 3 and then add 5 method? Well, we would want to run that in reverse. Since the last thing we did was add 5, to encrypt the message, the first thing we need to do to decrypt our message is to undo that last step, and the opposite of adding 5 is subtracting 5. So far, so good. Next, we would have to reverse the multiply by 3 step. Well, what's the reverse of multiplying by 3? Well, it seems like the reverse would be dividing by 3. But how would we do that using modular arithmetic? Let's pick one of the letters in our message that we were encrypting earlier and break down the steps that we did. When we're encrypting the letter T, we first find that T corresponds to the number 19. Our first step of our encryption method is to multiply by 3, and 19 times 3 is going to give us 57. Now, if we stopped at that point, if we just multiplied by 3, our modular arithmetic, finding our remainder, we would take 57 divided by 26. That's going to give me 2.192. I take the whole number part of that, multiply by 26. That gives me 52. And then 57 minus 52 is 5. So that's where this 5 is coming from. And if then I add 5, well, 5 plus 5 is 10. And that's where I'm getting my K as my encrypted version of the letter T. Now, if I want to reverse these steps, well, the opposite, as we talked about before, the opposite of adding 5 is to subtract 5. 10 minus 5 is 5. But now what we don't know is what the heck should this operation be? What do I do to the 5 to get back to 19? Again, thinking about dividing by 3 doesn't really make sense here. First of all, 5 divided by 3 isn't really typically thought of as a whole number, and how the heck would it work out to be 19? So something weird is going on here. So instead of trying to divide and getting fractions and having to worry about that, it turns out that the opposite operation for multiplying by 3 is actually to multiply by 9. So what we see here is, and again, here we're just focusing on the multiplication operation. If I take one of these letters, for example, let me take the letter E here. So if I multiply E by 3, so E corresponds to the number 4, 4 times 3 is 12. Now if I take that 12, and again, I'm not thinking about division here, I'm thinking about multiplication. If I multiply 12 by 9, again, grabbing my calculator, 12 times 9 is 108. 108 isn't between 0 and 25, so I've got to use modular arithmetic. So 18 divided by 26, sorry, 108 divided by 26 is 4.153. I take the whole number part of that, multiply by 26. That's going to give me 102. Sorry, 104. And then I subtract that from the 108. 108 minus 104 is giving me back the 4 that I started with. So when I do these two multiplication operations in sequence, the end result is that I get back to where I started. I start with 4, I multiply by 3, I get 12. I take 12, I multiply by 9, I get back to 4. So these two sequenced multiplication operations get me back to where I started, get me back to my original alphabet. So why did that work? Why does multiplying twice and not doing any division at all, why does that get us back to where we started? Well, let's look at those numbers that we multiplied by. We multiplied by 3, and then we multiplied by 9. And if you notice, 3 times 9 is 27. And in this modular arithmetic, where my modulus is 26, 27 is really the same as 1. So really, we're multiplying by 27, but that's the same as multiplying by 1 in this weird modular arithmetic system. So what we would say is that 3 and 9 are multiplicative inverses modulo 26. So when we multiply by both of those numbers, it's like we didn't multiply anything at all. And multiplying by 3 and multiplying by 9 are these inverse operations. These two operations undo each other. They are the reverses of each other. And finding these inverse operations is really the key to using multiplication to encrypt and decrypt messages. But not every multiplication is going to have an inverse. Let's take a look at multiplication by 6. So again, here's my original alphabet. And if I multiply by 6, let's look at B and O here. So B corresponds to the number 1. 1 times 6 is 6. O corresponds to the number 14. What's 14 times 6? Well, 14 times 6 on my calculator is going to give me 84. But 84 isn't between 0 and 25, so I've got to use modular arithmetic. I'm going to take 84 divided by 26. Again, on my calculator, I get 3.23. I take the whole number part of that, multiply by 26. 26 times 3 is 78. And then I subtract 84 minus 78 is 6. So in this multiplication by 6 encryption method, both B and O get transformed, get encrypted as the letter G. But then how would we decrypt a message like that? If we received a message that was encrypted with this message, and the encrypted message had a G in it, how would we know how to decrypt that G? How would we know whether that G corresponded to a B in the original message, or whether it corresponded to an O in the original message? There would be no way for us to know. So this multiplication by 6 method doesn't have an inverse operation. There is no way to reverse that multiplication. So how would we know in advance whether a particular multiplication operation is going to have one of these inverses? Well, whenever we multiply by a number that shares a common factor greater than 1 with the modulus, it turns out that that operation will not be invertible. So in our multiplication by 6 example, 6 and 26 share a common factor. They're both even. They're both divisible by 2. And so that's what turns out to be the reason why multiplication by 6 is not actually invertible. Now, a prime number is a number where the only divisors are 1 and itself. So if the modulus is prime, then it'll be pretty much impossible for the number we multiply by to have a common factor with that prime modulus. So 26 is not prime because it's even. As we just saw, it's divisible by 2. 27 is not prime. Its divisors are 1, 3, 9, and 27. 28 is not prime because 28 is also even. But 29 is prime. The only divisors, the only numbers that go in evenly to 29 are 1 and 29. So let's use 29 as our modulus. So let's try this. Let's encrypt this message, retreat at once, using multiplication by 6, right, which we knew was problematic before. But this time, we're going to use the modulus of 29. So I'm still going to replace my alphabet by numbers, just like we did before. So I've got my alphabet written out, and I've got the start of my message. Again, I'm just going to do the first few letters here, but then I'll show you the solution on the next slide. Okay, so what do? So I start by figuring out what number corresponds to the first letter of my message. Well, that's going to be 17. So I'm going to use multiplication by 6. So I'm going to do 17 times 6. On my calculator, that's going to give me 102. Now, I'm working modulo 29 now. So now I need to use my modular arithmetic if the result I get is bigger than 29. So since 102 is bigger than 29, I'm going to take 102 and divide it by 29, right? Normally I would be dividing by 26, but this time we changed the modulus. So 102 divided by 29 is going to be 3.517. But just like before, we take the whole number part of that, we multiply that by the modulus. 3 times 29 is going to be 87. And then we subtract 102 minus 87 is going to give me 15. So 17 gets encrypted as 15. E corresponds to the number 4. 4 times 6 is 24. That's less than my modulus. That's less than 29. So I don't need to do any division. I just have that encrypted as 24. T, let's do one more here. Let's do a couple more actually. So T is 19. Again, my operation is going to be to multiply by 6. So 19 times 6 is going to be 114. And that's too big, so I take that divided by 29 is going to be 3.93. I take the whole number part of that, 29 times 3. That's going to give me 87. And then I subtract 114 minus 87 is going to give me 27. Now here's where we see a problem with this method. So if I wanted to turn my encrypted message into letters, I can do that at first. 15 corresponds to the letter P, 24 corresponds to the letter Y, if I see over here on my alphabet. But 27, well, that's bigger than 25. That's bigger than the number of letters in my alphabet. So I don't have a letter that corresponds to the letter T to replace that with. So that typically means that when we're using this kind of method, rather than having our encrypted message be also made of letters, instead we're just going to have our encrypted message be made of numbers. And so again, when we find the reverse operation, which we'll talk about in a second, the reverse operation would just take these numbers and turn them back into the original numbers in my message, which will turn out to be 17, 4, 19, 17, and so on, which we can then use our alphabet to turn back into letters. So when we use these multiplicative and affine ciphers with a modulus greater than 26, as we just said, we're going to simply leave our encrypted message as a sequence of numbers. And that actually also allows us to encrypt messages with more kinds of characters, right? Not just letters, but in capital letters and lowercase letters, numerals, symbols, spaces, and so on. But the difficult part of using these ciphers is finding the inverse of the multiplication operation. So our big question for the cipher that we talked about in the previous example would be, okay, we multiplied by 6 modulo 29, but what would be the inverse of that? What would be the multiplication that would take us from 6 back to the original message? So that difficulty is actually a potential advantage. We can even make the encryption method, this multiplication number, in our example 6, we can make that number public. And if the numbers are large enough, it actually can be really difficult to find the inverse operation. There are a couple of methods that can work, but ultimately it comes down to mostly guessing and checking. Again, when the numbers are very, very large, it's hard to know, even when you know the number that you're multiplying in the first step, what that second step, what that reverse operation would actually be. And like I said, in the next lecture, we're going to talk about how that actually can be turned to our advantage to help make our encryption methods more secure.